So that's a great pleasure to have Patrick O'Ryan to give this talk. In fact, the pleasure is also to have Patrick O'Ryan among us here. And I hope also in the future year, things is not sure, but we are all working for this possibility. Patrick is giving a very relevant intellectual, and not only intellectual contribution to the group. It is here by a lot of discussion with students and with colleagues during seminar and also during beer events, especially the most important moment, of course, that every one of us know. And Patrick is also the person that will give the introduction of philosophy class for MPP student next term. So it will also contribute, I would not say in a greater way, because the contribution is already great that he does, but to say in a more official way to the MPP adventure. So you should know that Patrick received his PhD more or less 1 year ago, correct? A little bit less, possibly?
Oh, yeah, officially in May or something, but
okay,
it's been done for a while.
Okay, it's done for a while, so let's say 1 year ago, from the University of Berkeley, where he worked under the direction of Paolo Mancosu and he was...
Yeah, Schmid Gupta.
Gupta, exactly. And what we present today is partly taken by his PhD, but also in perspective of a future publication, I think. Okay, so,
all right.
you know the rules.
I know the rules. So, yeah, I've
Is recorded.
I think you started recording.
Is recorded?
No?
Is not recorded?
Oh, yeah, it is. It is.
Recording.
Yes. It's up.
Okay. Go.
Okay, great. Right, yeah, so the rules are people can interrupt me at any time to ask a question, which should be fine. I've actually taken a different tack here. Many other people had shorter talks. This one is very long, so that's going to try to motivate me to push through questions a little more. But yeah, what I want to talk about is both some past work of mine and current and hopefully future work. But really, I want to articulate kind of a broader project that I think many people can participate in. And so that's why the talk is a bit long, and I try to give quite a bit of background as to how and why I'm thinking about these problems. So, okay. So the first aim of the talk is just to investigate the role that infinity plays in establishing results about finite. And I guess initial distinction I should make is I'm just taking the sort of cutoff point between finitary and infinitary mathematics to be following. So consider first order piano arithmetic finitary. In particular, that's bi-interpretable with Zermelo-Frankel set theory without the axiom of infinity and with the negation of the axiom of infinity. So hereditarily finite sets. I'm taking that to be what classifies finitary mathematics here. Of course, there are many questions about what finitary mathematics is, especially in connection to Hilbert's program. But this is just what I'm fixing from the start. And anything beyond that should count as infinitary mathematics. Okay, so that's what I mean when we're using infinite resources to establish results that live here or lower.
So make a remark that they seem to make. It's not really a question, but it would be surprising to be wrong, but possibly I'm wrong. So first, an objection that one can make to this idea is to say, but how is possible that with the negation of the axiom of infinity, we double interpret PA, where then we call the natural number form an infinity set?
Yeah.
And I think that the answer is that in PA, there are individual natural numbers, but there is nothing as the set of natural numbers.
Right. Yes. I think that is the answer. It's actually rather an interesting question, the nature of the interpretation going this way. from PA to this theory, there's an interpretation by Ackermann, which is used pretty consistently. But there's a recent paper that shows, yeah, actually getting the details of this interpretation correct, it's a little subtle. So I think that's part of your question, Marco. But yeah, what you say, I think is why this makes prima facie sense.
Is that the K and Wong paper going to?
Yes, yeah. So I mentioned this yesterday in discussion. So it's a paper by Kay and Wong. It's quite interesting because this result is, they call it a folklore result, and it is true. It was hard to pin down exactly where you find proofs for the by interpretability. So they investigate that in some detail. It's, quite interesting. But that's what I'm taking to be the cutoff point. So I want to argue that using infinitary resources is in some sense necessary, and the sense of necessity will be clarified. So let me leave that for now. And then the larger project is to just show how this question or these questions about how the finite relates to the infinite can inform and enrich other debates in philosophy of mathematics, especially what's called philosophy of mathematical practice, which is not a term I particularly like actually, but that's kind of where the debates live, especially about explanation and purity. So I think all of these different distinctions intersect in very interesting ways, and we haven't really thought about that nearly enough. So I use what's called Gödel's doctrine as sort of a starting point, and I'll give the statement of his doctrine in a second, but he claims that as a result of the incompleteness theorems, infinitary mathematics is necessary to account for finite mathematics. And I take it what he means here is it's proof theoretically necessary. In order to get proofs of particular finitary statements, like consistency statements, you actually need axiomatically strong mathematics to do that. Okay. However, there's a lovely paper by Solomon Feferman. I think it's called "Is Cantor Necessary? Infinity in Mathematics" or something like that, where it's about 100 pages, and he spends a long time very carefully looking at various proof theoretic results that seem to undermine Gödel's claim. And so I want to look at these arguments in a little bit of detail. Right. So in order to understand Feferman's arguments, we need to look at a class of finitary statements that are proved using infinitary resources. So there are two main varieties. So the first are independence results from logic, and these are the things that come out of incompleteness. And I'll talk about some famous examples here. But I also want to look at results from more ordinary mathematical practice, in which you have a finitary statement that has multiple proofs, right? And some of the proofs might employ infinitary resources. And I want to see what that is actually doing in practice, right? Is the infinite here necessary in some sense for conviction, explanation, maybe some sort of heuristic guidance? I think there are a number of ways we might understand that. Okay. Right, so the independence results have received quite a lot of attention, but the slides still.
You do not see the slides?
Alex?
Valeria, you do not see the slides?
That's right. I cannot see the slides anymore. They were showing before, but now I can only see the room.
Okay, so thank you for telling us.
Okay.
We
Thank
try
you.
to solve the problem.
Oh, it seems that we are not connected here.
I can see the slides here on my screen.
You can see.
Yeah.
I see the slides.
Slides. Oh,
I'm so sorry. Then maybe it's my thing that's only not showing the
Say
slides
that-
anymore.
say. So possibly it's a problem from your computer, Valeria.
That's right. There must be a problem with my computer. Sorry about that.
Thank you in any
No,
case.
thank you. Yeah, I'm sorry. Hopefully, verbal is enough. Right. Okay. So I already mentioned this briefly. The sort of latter results that I want to look at, where we have a finitary statement that's proved using infinitary resources, but not necessarily so. I think this can inform debates in questions about purity, impurity, explanation, lack of explanation. Also questions about simplicity. What kind of simplicity and the role of simplicity in mathematical proof. So I'm going to focus on these two axes in the talk. Right, so we want to ask what is actually gained epistemically when we have such a situation in mathematical practice. Right, and just methodologically, the independence results are very interesting, and I am going to spend a good deal of time talking about them. But having results with multiple proofs allows for us to do a lot of interesting comparative work, which is actually quite useful philosophically. Sometimes independence results, it's hard to say much about them philosophically because you can't do this kind of comparative work. So this is one advantage of looking at this other class of statements. And I'd like to conclude, I don't know if there will be time, but just mentioning some additional case studies that I want to undertake or am undertaking, and possible metaphysical implications for this discussion. I'm remaining pretty epistemic here. This is very much a question about epistemology of mathematics, but I think there are ways to talk about canonical debates.
So when you wait to speak in metaphysics when I go away.
Yeah,
When I am not here, you speak of metaphysics.
Yeah, well, I'm somewhat less interested in the metaphysics, but I'm interested enough. I'm a philosopher, so I feel like I should say something. Right, and yeah, again, just methodologically, I think a fusion of techniques from philosophy, sort of first order mathematical practice, and mathematical logic is actually a really informative way to do philosophy of mathematics. So that's what I'm trying to do. Okay. So yeah, just to introduce very briefly the incompleteness phenomena. Of course, these theorems hardly need any introduction, but I'm going to just introduce them anyway. Before the whole point here is that Gödel produces sentences of finitary character, right? True sentences stateable in first order piano arithmetic that require something more to prove them. Right? So the first incompleteness theorem shows that there's this called the Gödel sentence G that informally asserts its own provability, but that equivalence in this theory T is what that actually means. And then we can show that T, if it's consistent and has sufficiently much arithmetic, can't prove G. And under some kind of finicky additional assumptions, I think Gödel uses omega consistency, but you don't actually need it. You can show that T also doesn't prove the negation of the Gödel sentence. And then the second incompleteness theorem tells us that, again, if we have this consistent formal theory with sufficiently much arithmetic, it can't prove its own consistency, where that notation, just if people are curious, consistency statement for piano arithmetic looks something like this. For all natural numbers n, it's not the case that we have a code for a proof in piano arithmetic that concludes with some sort of contradiction. And I'll mention this now because some of the Feferman stuff mentions this. This is what's called a pi01 statement. So it's pi because we start with a universal quantifier. We're quantifying only over natural numbers, not sets of natural numbers, and we have one alternation. Right, so in particular, piano arithmetic doesn't prove its own consistency. And this is the kind of start of these questions.
And that's because all the other quantifications that go on in the provability predicate are bounded.
So the
Because
provability.
there are other quantifiers appearing in the form.
That's right, yeah. So it's, so this is a primitive recursive, bounded quantifiers, right?
Okay.
Yes. Yeah, so
That's why the one, it's not larger.
Exactly. Yeah, so typically when we write, so if we were to write it more abstractly for all n theta, you would say this is pi01 theta has bounded.
Yes.
Right. Okay. So this is now what is called by Feferman Gödel's doctrine. So Gödel says the following in a very surreptitiously placed footnote, I think after he proves the first incompleteness result. Says the true reason for the incompleteness inherent in all formal systems of mathematics is that the formation of ever higher types can be continued into the transfinite. For it can be shown that the undecidable propositions constructed here, just thinking of consistency statements, become decidable whenever appropriate higher types are added. An analogous situation prevails for the axiom system of set theory. So, as much of what Gödel says, this is a little cryptic, or you have to fill in some of the details. But I take it in this in the second sentence, it can be shown that the undecidable propositions are constructed here become decidable. What he's alluding to here is that in a higher order extension of a given theory, you can define the formal truth predicate for the theory and the set of true sentences in the theory, and then prove a consistency result from that. You might even you might make this a little fancier. It's actually not terribly relevant here, but if you look at the impredicative second order axioms for Peano arithmetic, that can prove the consistency of the first order versions of the axioms. Okay. Right, and yeah, this remark appears in a footnote, but it's really quite central to much of what he does later in set theory. So there's this Gödel's program for adding, what are now called large cardinal axioms to Zermelo-Fraenkel set theory to try to decide, well, in particular, the continuum hypothesis, but you might look at other undecidable statements. So I take it that's somewhat implicit in this little statement. Okay, so in Feferman's essay, he glosses Gödel's quote as saying, "The unlimited transfinite iteration of the power set operation is necessary to account for finitary mathematics." And Feferman does not like this because he wants to challenge it when you read it as saying the Platonistic view of the determinateness of the power set operation and its iteration through all the ordinals is necessary for the derivation of previously undecidable but true pi01 sentences. So Feferman's idea here, which he spells out in a few places, is that even one iteration of the power set on the natural numbers requires some implicit commitment to Platonism, because he thinks nothing else can justify believing that that set is actually a determinate set. Which
So Feferman is denying the green one. The point of Feferman is that the green one is a
Right.
compressible interpretation of the blue,
right.
and so the green is false, and also the blue is false. That
Yes.
this is the point.
Yes, that is the point. This is ultimately what he's driving at. His essay is also not particularly metaphysical. It's actually a bit difficult to read because he doesn't make this particularly clear throughout. But if you kind of triangulate from other writings of his, this is what he means. There's a famous paper of his where he talks about the continuum hypothesis not being a definite mathematical problem. It's a similar idea. I mean, yeah, even worse in that case. But he thinks, even one full iteration of the power set on the naturals can only be justified by Platonism, which is a bit of a weird. I'm not totally sure if I buy that. It's not necessary to get too deep into that now, but you might just take a more kind of naturalistic view and say, why can't we have some belief in the determinateness of the power set given what we do in mathematics? But in any case, and of course, he doesn't think Platonism is a reasonable philosophical position to have. Right. And he uses this phrase, a medieval metaphysics of mathematics, which I really like. And this comes from a Weil quote in which Weil is talking about mathematical logic being sort of stuck in the Middle Ages, in a very long Middle Ages, because of the acceptance of the higher infinite. So,
what year is Feferman's paper?
I think it's originally from the late 80s. There's a collection called In the Light of Logic, which is from 98, I think. There's kind of a revamped version in there. So that's.
No, but the paper by Feferman is before.
Yeah, the original paper is before, but it does have some significant changes. Yeah.
I remember a paper by Petitot in the 80s that was discussing this point of medieval metaphysics. So,
by
Petitot.
Oh, yeah, okay.
It was in the end of the 80s, so the paper should be 85, 80s.
I think it might have been like 87. Yeah.
Yeah, something like
It's hard to find that. The original version
Yes,
is a bit hard to find.
something
So.
like that.
Okay, so yeah, this whole essay is driving towards undermining Gödel's doctrine, in particular this Platonistic construal of it, which didn't seem to be Gödel's view in any case. Okay, so the argument proceeds as follows. So first he just considers the consistency of piano arithmetic. And he shows that, looking at this result that I said was implicit in the Gödel quote, that in predicative second order axioms, so second order piano arithmetic, that should prove consistency of piano arithmetic, which is not very surprising. But what Feferman wants to say is, well, you can get away with less than this result is saying. In particular, you don't need the full power set. And so he goes through that derivation. I think he shows, people who are curious, I think he shows that delta 1-1 comprehension is enough, but actually you can get away with even less. I'm not totally sure why he doesn't do that, because he certainly knew about it. But, so that's sort of the first stage, is to show that even with the statements with which Gödel was initially concerned, this doesn't really hold water. And then second, he tries to reinterpret Gödel's doctrine using less wasteful resources, maybe. So one way is he says, okay, the true reason for incompleteness is actually Tarski's undefinability theorem, right? You can't actually express the truth definition for a particular language in the language itself. And then his proposal is that, well, if you informally acknowledge the consistency of a theory, why not just write down some informal truth predicate with appropriate closure axioms, adjoin it to the theory, and deduce the consistency. Again, it's a little bit, yeah, I would have liked him to say more, but that's supposed to be the basic sort of idea. And then he also says, well, you could do it in terms of reflection principles, which are, it's supposed to be an expression of our, again, informal acceptance or faith in the consistency of a theory. So he says, just adjoin reflection principles to a given theory. From there, you can prove consistency statements. And in either case, you don't need all these higher types when thought in terms of set theory.
So how do you read these kind of brackets?
That's the Gödel number 4.
So if you have a sentence A in your theory, the corner quotes or the Klein quotes or Gödel brackets is saying that's the Gödel number that codes the statement A.
The numeral. The numeral.
Yeah. That's right. There are no numbers.
There are no numbers.
There are numerals. Yes.
Okay. So to sum up here, it seems that given Feferman's arguments here, Gödel's doctrine fails. Okay. Somewhat worse is that you could even say, well, the kinds of pi01 sentences, the kinds of results that we're looking at, are they kind of have a cooked up look to them, right? So the Gödel sentence has this sort of self-referentiality to it. You might even worry about the coding. This has kind of been a point of contention when thinking about the relevance of these results for ordinary mathematics. And Feferman seems to take this quite seriously. Here's an especially strong view, which I think is far too strong, but by Angus MacIntyre. So he says, in central parts of mathematics, one does not go looking for monsters, and one does not encourage them to intrude. One of the most deplorable effects of Gödel's work is the fixation with examining phenomena in utmost generality in territory far beyond mathematical civilization. So, yeah, that's a rather funny quote. I don't agree with that, but anyway. But given
MacIntyre's not usually funny, so
no, actually, this is from
noteworthy for that reason.
This is from a paper called, I think, The Relevance of Incompleteness for Mathematics. And he goes on like this at some length. Anyway, so given these sorts of concerns, you might ask, well, can we produce more natural looking results? Namely, results that look a little closer to ordinary finitary mathematics. As we'll see, you can of course question the relevance of these results, but this led to a whole kind of cottage industry in the 70s and maybe even earlier in trying to produce such results. So one of the most interesting, one of the first, I guess, comes from Ramsey theory, which very broadly speaking is trying to find structure within disorder. So in 28, Frank Ramsey proved this theorem, or this, what this says with this arrow notation is that if we have a set S and the size of S is big N, then if we color the set of p-sized subsets of S, usually written like this, with R colors, you'll find a monochromatic subset of size K. Okay. I'm actually astonished. I was able to remember that. I always get this confused. I think that is correct. Right, and so yeah, again, just following the kind of main idea. This is the sort of ordered structure inside of a sufficiently large set. So this on its own is provable in Peano arithmetic. And here's a particular illustration to try to make it a little more concrete, which is the theorem on friends and strangers. So the story is that, yeah, you walk into a party and the question occurs to you, when will it be the case that three people either know each other or don't know each other, right? And so if you express this in terms of Ramsey theory, so you're looking for a set of size 3, right? When you two-color a particular ambient set with knowing or not knowing each other, right? And you examine people pairwise. And it's the case that you'll find a monochromatic subset, or a set of people who know each other or don't know each other, when the size of the initial set is greater than or equal to 6. Okay, so you can see it in this illustration. So you can see a blue triangle there. So let's say those are the people that, I don't know, blue seems friendlier to me, so let's say they know each other. How about that? But as you start increasing the size of the parameters, these questions become extremely difficult. And so in particular, you produce these kind of beautiful graphs that represent the situation, but they're very hard to analyze. So I think this is a two-coloring 24 nodes in this graph. In any case. So the modification of finite Ramsey's theory.
So, come back there, let me understand better. This means that if you color anything in blue or red, of course, the theorem is true because all of them are monochromatic.
Okay.
So the idea is that if you decide that there is some segment in red and some segment is blue, necessarily there will be a triangle that is all blue or all red.
Provided that you are looking at least 6 things. Yes, right.
It is particular cases.
Yes.
There is no way to color into different colors in such a way that at least the triangle, there is no one triangle that is all red or all red, all blue.
Mm-hmm.
Yeah. In this case, there is one that is all, no, 2, 3, no, 2 that are all blue. Okay.
Yeah, I see 2.
2 that are all blue.
But yeah, you could provide other colorings, but yeah, the point is you'll never avoid either a red or a blue.
Okay.
So the supposedly more natural independence result is this principle. I'll call this sort of a combinatorial principle by Paris and Harrington, which says that you just add the further requirement to the finite Ramsey's theorem that the monochromatic subset you find of size K also satisfies a further condition, namely that the cardinality of the set is greater than or equal to its minimal element. So when you add this requirement, this theorem is no longer provable in Peano arithmetic. And it's the requirement itself is so the claim was that this is a more natural statement, and I include it because I've looked at these in Ramsey theory, but you certainly might question whether that size requirement is natural whatsoever. I think maybe Harvey Friedman mentioned, he said there's something very weird about it because it's not properly typed, but you're using an integer to measure both the cardinality of the set with which you're concerned, and you're just saying that is the minimal element of that. So he thinks there's something very weird going on because of this failure of typing. But even if you don't worry about that, it's not clear that that kind of constraint would ever come up in the wild. And then this kind of opened the door to other results of finitary character that are independent of successively stronger systems, actually. So two of the most famous are Goodstein's theorem and finite Kruskal's theorem, which is a result on trees. Many of these results have a kind of constraint, like a cardinality constraint that seems to force the axiomatic strength of the theorem to be greater. I don't think Goodstein's does, but many of the others.
I think Friedman, if I'm not mistaken, it seems to me Friedman's objection is that this isn't invariant under isomorphisms of graphs.
Oh, maybe, yeah, okay.
Right, because if you change the coding, then you'll have a different minimal number in the monochromatic thing. And I think that was, if I'm remembering right, that was his worry.
Okay.
This is a property that's not natural because it's not invariant under isomorphism.
Right, and that's if anything's not natural, that would be it, yeah. Okay, no, that's helpful. Do you remember, Drew, where does he?
No, I'm sorry.
I mean, I going through this stuff is difficult.
I can barely remember where I left my keys. So.
Because I remember reading something like that. I just don't.
But also I mean, if you're really worried by that argument, you could just add some structures to your graphs. And then suddenly, right? So
yeah,
and that wouldn't affect the probability. So I'm not sure this is in the end a convincing.
Yeah, I'm just remembering that's what I remembered back then when I read this.
Why wouldn't that affect the provability if you had further structure?
I mean, just on the graphs, right? So because I mean, the text of the theorem wouldn't change. Just the definition of isomorphism would change.
I see. Okay.
Yeah.
And so it just would affect the definition of what is natural, right?
Right. So in any case, so now we supposedly have these more natural independence results. So Feferman has to deal with these kinds of things now. Okay. Right. So we already talked about this. But yeah, what Feferman shows, and this is a pretty big bulk of the paper, is that he goes through, I think, all of the existent ones at the time. All of these finitary combinatorial independence results often can be proved in much weaker systems than they are ostensibly proved in. And so he does something called proof theoretic reductions. And so even when you're dealing with like an impredicative system, he shows that you can often reduce to a predicatively justifiable system, where that means all the quantification over your sets. Each set is built up from previously given definable arithmetical sets. Okay, so he claims that this collection of finitary independence results doesn't actually support Gödel's doctrine. And this is very interesting, where it's really quite spectacular. And then I suppose I should mention there's also this program by Harvey Friedman in which he claims to have produced finitary results that actually require axioms beyond ZFC. Again, the exact status of this right now, I'm not sure, but if you start looking at these things, they really look bizarre. It's like not even fruitful to reproduce one here. So I'm not convinced here, but maybe others are. Anyway, so supposedly we've undermined Gödel's doctrine, and that's basically where the Feferman paper ends. The question I want to ask is, though all this is very interesting, maybe this focus on axiomatic strength and proof theoretic necessity is actually neglecting some important lines of philosophical research. Right, so namely, if we want an epistemology of mathematics that is adequate or approaching adequacy for mathematical practice, we should actually look at what is being gained epistemically when we're using infinitary stuff to prove finitary stuff. Right, and as I mentioned, we already get we get this nice comparative ability when we're not looking just at independence results. Although you can try to run this with independence results. So if you have that a statement is independent of Peano arithmetic, but say it's ostensibly provable in some stronger system, but then you reduce it to an intermediate system, you could look at what happens when you perform that reduction. My guess is that it will probably be much messier and nastier, but I'll talk more. Right, but I don't want to sort of throw out all of the results that we have from proof theory and computability theory that can help make this investigation in first order practice much more precise.
So now I would like to understand in a possibly more simple, intuitive way the basic point that you are making. Let's see whether I understood.
Okay.
Gödel doctrine is the idea that all the theorem, all the statement have G that cannot be decidable within Peano arithmetic first order require a proof that require infinite iteration. This is the doctrine.
Yeah, and so
the reason for which they cannot be proved finitary is that they require a infinite iteration.
Right. I take it what he's thinking is, yeah, you start with Peano arithmetic, and then for each stronger system, just look at the consistency.
And Sol's Feferman points is that there are cases of sentence as Parry-Huntington theorem that cannot be proved there, but still can be proved in a very weak extension.
Yes. Some sort of system that is,
so that does not go to go up
okay.
to the infinite.
Yes, exactly.
So the limit is not finite, infinite. This is the point.
This is the point.
Okay.
Yes. Yes. Perfect. Yeah. Yeah, that's the point. Okay, so I want now I want to sort of transition to some case studies from again more ordinary mathematical practice, but first a very recent result that requires quite strong infinitary stuff to prove is Fermat's theorem. So don't ask me about the actual proof of this thing because I have no idea. But the statement of the theorem just says.
I believe that you would have proved the theorem here.
Just
why you do not do?
Don't ask me anything about it, please. I can evaluate the strength here.
I had a very nice proof of that theorem, but I forgot.
You forgot. But it's too long and right in the margin of the book.
I was going to say, Jose, did you write this? So this is an image of Fermat's commentary on Diophantus's Arithmetica, in which he says that the margins are too narrow to contain this proof. Right, and as is well known, this was proved in '95 by Andrew Wiles with a patch by Richard Taylor, and it's just a famously difficult proof. But this is a finitary statement, so for n greater than 2, there do not exist 3 positive integers ABC such that that relation works. Okay, so very recently, let me get to that. So. Crazy people went through the proof and really tried to determine what exactly the axiomatic resources needed to prove it are. So the proof itself ostensibly goes beyond ZFC. And the point of contention is what are called Grothendieck universes. So these were provided by Grothendieck to serve as basically all the set theory he needs to do his algebraic geometry and number theory. Right, and informally they are sets large enough that the habitual operations of set theory do not go outside of them. And then he proves that U is a universe if and only if for some strongly inaccessible cardinal kappa, U is equal to the rank of the cumulative hierarchy of rank kappa. And this, you can show that this V sub kappa is a model for ZFC, and so by incompleteness, ZFC cannot prove the existence of the model nor the existence of the inaccessible cardinal. Okay. So people did this work. They went through the proof of Fermat's theorem and showed that actually we have these very strong axiomatic assumptions.
So that's precisely how it's stronger than ZFC? It needs strongly inaccessible cardinals.
Needs strongly inaccessible.
Okay.
Yeah. Or that was the claim. Yes.
Okay.
In the proof. Yeah, I think because there again in many message boards and just footnotes and articles, number theorists are always saying, yeah, you don't actually need that much, but they never provided evidence, which was annoying. And then Colin McClarty actually went through the proof, tracked down precisely where you need the existence of a Grothendieck universe. And then he undertook this very crazy project, which I'm not going to describe, that you actually don't need to go beyond ZFC to prove Fermat's theorem. So I think it's from 2020 or 2021, he shows that he doesn't call it simple type theory, but he calls it something else, but it's simple type theory that suffices to give you the proof of Fermat's theorem. And so that is still quite strong. So, but much less strong beyond ZFC. So it's like if we have second order arithmetic here, then we might have simple type theory, Frankel, ZFC, and then large cardinals. So he produces the needed axiomatic strength. The point being, though, this is still so strong that all of the results Feferman uses to reduce these stronger subsystems of second order Peano arithmetic no longer hold. So this is, in fact, seems a necessary use of at least, beyond one iteration of the power set on the naturals to prove a finitary statement, which is pretty, it's really very spectacular. His paper is also extremely difficult to understand, but at the very least, the hierarchy of what you need is clear. Okay, so it seems that we have at least one, I say undeniably natural and deeply important finitary statement that requires pretty strong infinitary resources to prove it. Undeniably natural. It's funny. I think there was a comment by Gauss when he was reading Fermat's theorem where he found it he didn't think it was important whatsoever. He said it just looked weird and cooked up. Who cares? Like, why study this? But then, I take it that the many hundreds of years of research and the connections to elliptic curves really, gave the Fermat's theorem its mathematical importance.
Okay. A simple type theory with infinity is something more than STT and less than ZF.
In terms of consistency.
Right. So you got it by STT by adding an axiom of infinity?
Yes.
But which sort of axiom of infinity?
Yeah, I don't know if he calls it finite order arithmetic. So he references something in the proof theory book by TQT that says, okay, it's simple type theory with infinity, but he has a whole formulation of this system.
In your second last bullet point, you used the word requires. Is that known that FLT requires this?
Yeah, so McClarty does show that this is best possible in various senses. So
But how do we know that that's
Yeah.
the proof? I mean,
that's true. Yeah.
it's the current proof analyzes to this being required for the current proof. I don't think
That's true. Yeah. Okay. Yeah. No, it's. So the phrase he does use is best possible, but you're right. We just
Yet,
find a,
this tells
Okay,
that
that's
there is
possible.
at least one proof
Yeah.
that does not require ZF. The wall in ZF.
No, but I take
maybe it's provable in PA.
right. Maybe
You know that.
Yes.
Right. Yeah.
Well, I mean, in principle, you could find a model of STT without infinity in which Fermat's theorem is false. Then you'd have your proof.
Well, I'm just asking what is currently.
I know. I'm
Yeah.
claiming that's.
We don't have such a proof.
You can see that Fermat's last theorem is actually independent of a weaker theory.
This is a very nice question. I think that we should invite Colin to come here as soon as
I think
possible.
that's good.
Colin was already here for the Grothendieck, you remember?
I think that's a good idea.
I will write to him.
And he didn't talk about this at all?
No,
during-
no,
Not-
he was
not at
taken
that-
to
not at that
something
point.
else.
Yeah. No, because it would be great to have some sort of just bullet point presentation of his paper if possible. 'Cause it's it's just difficult.
We will see whether there is a slot free in the.
Yeah, but I take the point. I suppose it's just like at this juncture, we don't have even the kind of result that Drew is gesturing at. So right, and actually that is related to this final point here. It's just that while we have one proof in fact, right, we show that it doesn't need as much axiomatic strength as initially stated in the proof. But for example, we have not done something where we try to formalize the proof in here, look at what happens, compare it to the original proof. That's the kind of work you would have to do to assess, is the large cardinal axiom actually doing something really, really, really significant in the proof? Is it structuring it in a particular way? Given the extreme difficulty of the proof of Fermat's last theorem, right, this doesn't seem. I don't want to say it's an infeasible project, but it's a very difficult project that we're not at all close to. And so, my move has been to consider things that we have a little more of a handle on.
And for your purposes, Aleph Knox that's infinitary. The accountable infinity, that's infinitary.
That's
Okay.
Right. So but it would have been remiss of me not to mention this recent work. It's really fascinating. Okay. So now I want to look at some other strands and think about how these questions about finitary and infinitary mathematics intersect with these. So two things we might ask. We might look at these questions about purity or impurity, right? So you might ask, why do statements about finite entities have these proofs that involve infinitary principles? And I think a very closely related question, which maybe is actually the deep question of purity and impurity, is what is the content of a mathematical statement? What is the mathematical content of a mathematical statement? And there are various ways you might try to make that more precise. I have a paper where I take some sort of stab at it, but it's quite hard. Similarly, we might ask, is there any relationship between pure and impure proofs and explanatory and non-explanatory proofs, right? So if we consider the use of infinitary resources to prove a finitary statement an instance of impurity, which seems a reasonable way to go, we can ask, what are the epistemic gains of that move to infinitary resources? Do we get a proof that is explanatory rather than non-explanatory, where you then obviously have to provide an analysis of what an explanatory or non-explanatory proof is, which is now a huge topic in philosophy of mathematics.
13 is Book of Infinity.
What's that?
13 is Paulo's Book of Infinity.
Oh, 13, that's the collection in philosophy of mathematical practice. Because you might ask, many of the distinctions made there, you might ask, about naturality. Is there some question about naturality that arises when you use infinitary stuff to prove finitary stuff? Is there a question about simplicity? All of these different axes of investigation that philosophers have looked at. Many of them seem quite relevant.
Have we seen a definition of explanatory proof?
No, not yet. I'm going to.
All right.
And
This is a great problem.
there is no even close agreement in the literature. There are many proposals. I'd be curious to hear, but at the moment I'm just indicating particular distinctions that might be connected to the finitary. So let's start with impurity. So very broadly speaking, an impure proof draws on resources that are foreign or extraneous to the theorem under investigation. So one way to think about this extraneousness is in terms of the topic or the content of a given theorem. So if the proof of a theorem tau is topically impure, then it's using resources where these might be definitions, axioms, inferential relations that are, well, I guess, yeah, inferential relations is relevant here, but yeah, definitions or axioms that don't seem to belong to the topic or the content of Tau. And so there's quite a bit of work on this by Andy Arana. And then Nick Detlefson also has some papers. And then you can also find stuff on this in Paulo's collection. Another distinction that Arana makes is between topically and elementally impure proofs of theorems. So you say that a proof is elementally impure if it draws on concepts that are less elementary or harder to understand than those that occur in the statement of the theorem itself. These two things are still incredibly broad and difficult to get a handle on. I take it that there's historical interest to the question because questions about impure proofs really were raised by Aristotle first. And it is just it seems to be a distinction that is made quite commonly in mathematical practice. So if you are trying to build an epistemology of mathematics, it seems that you should take seriously these evaluations of mathematicians. So that's part of the motivation for looking at purity and impurity. Right. So you might try to put it as follows. Topical impurity is a difference in kind, whereas elemental is a difference in some sort of strength. Either there's a more difficult, the resources required are more difficult to understand, or maybe you could just think about axiomatic strength. And the finitary, infinitary distinction, I think could be considered either topically or an instance of either topical or elemental purity. Okay, so.
Hello. There is also a notion of purity and impurity in proof theory that is much more concrete. You know, it's about using the sequent calculus and saying whether the operation was defined early on. So kind of a rule that uses things, introduces things both on the left and on the right is impure, and the rule that introduces things only on the left or on the right is pure.
Valeria, I am not able to tell anything clear about that. But if I believe to remember that Andy tried to do it and he failed.
Yes.
It seemed to me to remember that this was a suggestion that he was working on, and then for some reason that I'm not able to remember, he arrived at the conclusion that it was a way out. There was not a solution.
Andy, yeah,
Really? I don't think so. I mean, I thought that.
I cannot tell more. It's a vague remember that I.
Okay.
Yeah, I think this is one of his. I think this is one of his early papers.
Yes, it seemed to me that one of the early papers was exactly this one. To speak in terms of purity and impurity using a cut elimination.
Because certainly Andy knows,
rule of introduction, rule of elimination. And in the end, he arrived at the conclusion that he was not a good way to make the distinction. But this is all what I can say. I do remember nothing more precise.
I thought the young Italians, like I'm sorry, now I'm blanking on the name of the guys, but I thought they actually had made a good definition out of it.
Alberto Naibo?
Alberto Naibo, yes, correct. Okay. Naibo and the other one, Pistoni?
Pistoni, yes, Naibo
yes.
Pistoni.
I thought they had tried, and I mean, I don't know, maybe, I'm not.
That's right. That's helpful.
So,
does Francesca Poggilesi have anything on this?
Francesca work of explanation, but not about the purity.
Okay.
Francesca has different result about the theory of grounding using that, but
and she's so good.
Francesca has no real point about the purity.
Okay.
So just for me to understand a little bit better what this pure and impure means, let's see if this would be an example of an impure proof. One typical proof of the fundamental theorem of algebra uses Liouville theorem,
Yep.
right? That is a theorem of analysis. And then people claim this is a proof that uses resources of another branch. That should that be classified as
Yes.
pure
I think that would be, or that would be
This is a
Impure.
typical example that made
Yeah.
people make.
another.
When you use the but intermediary value,
intermediate value theorem.
the remedial value theorem to prove what is a very usual way to prove the fundamental theorem of the algebra.
But I wonder whether
And this is one of the classical examples of impure.
But it's a very difficult question because it's ultimately going to be based on the content of the theorem, and yeah, how do you ascertain what the content is? There's an example. Actually, I'm going to talk about Furstenberg, but by Hillel Furstenberg, he gives a topological proof of the infinitude of primes.
yes.
You might think that's pure if you think that the natural numbers have implicit topological structure, or if you don't think that's the case, then you might think it's impure. Another kind of classic example is, again, Andy Arana talks about this as the prime number theorem. So proved initially using
Prime number theorem.
so it says like the prime counting function grows as x over x. So this was proved in the late 19th century using complex analytic techniques, and in particular the Riemann zeta function. Properties of the zeta function are key to this. And then in the 50s, it was proved by Zellberg and Erdős using really, nothing more. I think they say nothing more than the properties of the natural logarithm. So that's supposed to be a canonically pure proof, and the
Another
complex
example,
analytic is canonically.
another example that Andy worked on is the fundamental theorem of arithmetic. That he showed that there are different proofs that are impure and other that are pure, but that there are some advantages. This is another example that he worked on.
Yeah, and I guess the difficulty that he probably encountered with using the sequent calculus notion of purity and impurity is that the judgments of mathematicians are not always very consistent, and he's always trying to adhere very closely to what the judgments are. And I mean, that's a question in these kinds of projects. Yeah, how close do you want to stick to what is being said?
Okay.
Great. Okay. And so it was Naibo and Bistoni?
Yes, possibly, yes.
Okay. So sort of the first intersection between these different distinctions that I want to look at is that between purity, impurity, and mathematical explanation. So this actually goes back to Aristotle. But we need to make a few qualifications first. So I've been understanding impurity, purity as properties of proofs, and similarly here I understand explanatory power as a property of proofs. But this is not necessary, right? You might examine these distinctions in terms of conjectures, definitions, all sorts of different mathematical statements. So this is you might also think that, explanatory power in particular is a property of a larger mathematical theory. So that would be a more global conception of explanatory power. But I'm just concerned with proofs at the moment.
What is nice is that we just mentioned Alberto Naibo, and I hear a mail by Alberto Naibo with the title "Possible Visit to Chapman in
Oh,
Germany."
good, yeah.
So Chapman is the center of the world.
Good job, Marco. And I'm interested in the notion of mathematical explanation where we're using mathematical facts to explain other mathematical facts. So this is an internal conception, because you might think that mathematical facts serve some sort of explanatory role in the natural sciences. So that's not the notion I'm concerned with here. And finally, I don't really want to lay down any a priori constraints on what counts as an explanatory proof, but rather I would like to follow Andy's example and extract what counts as explanatory proofs from case studies based on plausible intuitions. So the Aristotelian point is that we have proofs of the fact, hoti proofs, versus proofs of the reasoned fact, dioti proofs. Namely, the proofs of the fact merely give us warrant for the truth of the theorem, whereas others provide the why of the theorem. And so this is taken now to be a distinction between non-explanatory and explanatory proofs. and again, it seems these are very sort of well, Aristotle doesn't make them so squishy, but they're kind of squishy distinctions, but they do seem important in practice. And so as a philosopher, you want to try to make sense of these. And in particular, this seems to make sense of perhaps why we keep reproving mathematical theorems, which was a topic that came up in Alex and Drew's talk. And maybe we have a proof of a theorem that, we believe it's a perfectly good proof, but it doesn't really give us any insight into why the theorem is true. And so we want to provide a more explanatory proof. And actually, Aristotle posited that it was necessary to have a pretty strong purity constraint on your proofs in order to produce an explanatory proof. So he actually has a position about this intersection between purity, impurity, and explanation. Okay, so now I want to look at an example. So what do we want? Just kind of zooming out meta-theoretically and looking at the kinds of things we want to analyze philosophically. So we would like finitary statements that have infinitary proofs, sort of naturally occurring infinitary proofs, which we can take to be a particular instance of purity, either of the topical or of the elemental kind. Again, we want multiple proofs so we could perform this kind of comparative work. It would be very nice to look at proofs that are subjected to some mathematical analysis so we can make some of our claims more precise. And then, another question, it would be nice to look at theorems that have some sort of acknowledged mathematical import, because you might think this will help you generalize what you're saying, or at least beef up your claims that what you're saying is important to mathematics.
Could you say something about what you mean by meta-mathematical analysis?
Oh,
Or are you going to go into that?
No, just kind of what we were doing earlier.
Okay.
Right, so, okay, do we have some sort of result that shows us this particular theorem in ordinary mathematics is equivalent to some subsystem of second-order Peano arithmetic, right? This is where the reverse mathematics comes in. It's very useful.
Yeah, I have a question with respect to the first bullet point. So if you have a finitary statement, but an infinitary proof, right? And you have a finitary statement and a finitary proof. Is there some prejudice about which proof explains more? I mean, do you expect a relationship between...
That's where I'm driving, yeah. I want...
Because I wouldn't, so...
You wouldn't, okay, yeah.
I'm wondering, okay, well, if you're saying you're going there, I wait.
That's where I want to go, yeah, that's where I want to go, but... ultimately what I want to say is that, oftentimes going impure, and in particular infinitarily impure, will help you get a more explanatory.
Okay. Yeah.
Which actually, is cutting against what Aristotle claimed, and many people claim for a long time.
But you have my support.
Okay. I'll try. I think I have a reasonable
I'm curious, yeah.
So, okay, so I have been working on this theorem, the Moradius theorem, which is, I guess it's kind of a Ramsey theoretic result in which we're looking for a structure inside of a disorder or randomness. So here's the statement, but basically all this is saying is if you have some subset A of natural numbers 1 to n, and this subset is sufficiently dense in the set, then the sufficiently dense set will always contain a k-length arithmetic progression, where an arithmetic progression has this form. So that's the structure inside the set on which we lay down very few constraints. It just has to be sufficiently big in this sense of density. Just to give an example of like a set that's not, so the primes, for example, are sparse in the naturals. Those don't satisfy a required density condition. Right. This is the theorem under consideration. So this is actually...
Can a moment? Okay. Amy,
Yeah, and
Amy that I wanted to, okay.
Yeah, and sometimes you'll see this, I say, it's sometimes stated in such a way that conceals all the different parameters, but I think for our purposes, it's best to. Okay. So yeah, this is an interesting and desirable case study for a number of reasons. So first, we have many proofs of it. So the original proof is combinatorial and finitary, which was given by Zemmeretti. Yeah, okay, so 7 years later, Hillel Furstenberg gave a proof using ergodic theory. And the idea here was to sort of mimic the presence of arithmetic progressions in these subsets of naturals in the setting of measure-preserving systems. So you have some set X, you have a transformation on the set T, and a measure. And it's measure-preserving in the sense that the measure of a set E, which should be a rel subset X, is the same as the measure of so the transformation is not changing the measure of any of these subsets. And the transformation T essentially just mixing up the elements of the subsets. And so Furstenberg's idea was to mimic the presence of the arithmetic progression using recurrence results, where you apply the transformation T, and so you have a recurrence of iterations of T on the set. So that's the basic. That was the first basic move. I'll talk more about it. So the point here is that the pure finitary proof is acknowledged to be just extremely difficult. In particular, there's a highly nonlinear proof structure. The results are interlocking in the sense that there are lots of different kind of internal connections between the epsilon delta parameters that you have to manipulate. There's really no reasonable simplification in almost 50 years, which is quite rare. So for example, it's reasonable to compare it to the Green-Tau theorem, which says that actually in the primes, you can find arbitrarily long arithmetic progressions. That was proved in the early 2000s. It kind of immediately received a much cleaner proof of that result, which is surprising because the primes are not a sufficiently dense set. So even this thing that seems like it would be harder has this much simpler proof, whereas the Zemmeretti proof, it's pretty intractable. And actually there was a whole conference at Berkeley, I think led by Tao, in which he tried to provide what he claimed to be some sort of simplification, and nothing really came.
But the case of the prime is not very surprising because the prime are less than the number, but they meet much less combinatorial. You can combine in. Maybe,
but yeah, you might also think that because they're like so in the Green-Tau theorem, kind of what you do is you have to deal with the sparseness of the primes and like project it down into a Zemmeretti type result. You might think that whole process, it's really very difficult. You would think that would be hard to simplify in any reasonable way, but I think it's a paper by Fox and Conlon maybe, where they give what they claim to be much proof. I just take this to be kind of interesting evidence for the difficulty of the Zemmeretti proof.
What do you mean by the an arithmetical progression with prime numbers?
Yeah. So you can. I think the
primes, but there was also a length 3 arithmetic progression, and there's also a length 4.
Yeah. So you say ins primes. There's a k length arithmetic progression.
So at this point is what is an arithmetical progression with prime? I suppose that is arithmetical progression with elemental primes.
Yeah, it would have to be. Yeah.
So I don't understand it completely well, because by an arithmetical progression, what I understand is a progression in which it's an infinite sequence in which every term is the previous one plus
some fixed
number. Here, as are not infinite arithmetical progression, are segments of the arithmetical progression.
Okay. Yeah, they're about
of a certain length.
Yeah. Right. So this is important.
So there's infinite sequences.
Yes.
Yes. I see.
Right, and actually there is some very nice metamathematical work by Jeremy Avigad on the ergodic proof. And this actually has caused me quite a headache because there was a paper in which he claimed that a key theorem in the proof is quite strong. So in particular, he claimed that it's equivalent to pi 1 comprehension, which is an impredicative system and pretty high up in this hierarchy under second order Peano arithmetic. And that's proved in arithmetical comprehension. So he stated this as a theorem in a published paper, but actually only one direction. He's only comfortable now asserting one direction of the equivalence. So this is open, and if anyone would like to prove the other direction for me, that would be lovely, because then I could use that. But in any case, again, this is part of what we're after here, because if we could find that, oh yeah, we require impredicative resources, that would give us sort of purchase against a lot of what Feferman is saying. And then, finally, the ergodic proof is favored by mathematicians for its clarity, and I've just tried to kind of unravel the proof from conceptual stuff. So next, I think I have so this is a picture that Zemaretti included in his original paper, indicating the kind of proof structure, and it actually kind of gives you a decent sense of how nasty it is. And it's also just very rare for a mathematician to include kind of diagrammatic representation of the steps of the proof. And here's Tau on Zemaretti's theorem, which I think is very informative. So the original proof of the theorem is a remarkably intricate piece of combinatorial reasoning. Most proofs of theorems in mathematics, even long and difficult ones, generally come with a reasonably compact, high-level overview in which the proof is conceptually broken down into simple pieces. There may well be technical difficulties in formulating and then proving each of the component pieces and then fitting them together, but usually the big picture is reasonably clear. In contrast, the pieces of Zemaretti's proof are highly interlocking, particularly with regard to all the epsilon-type parameters involved. It takes quite a bit of notational setup and foundational lemmas before the key steps of the proof can even be stated, let alone proved. Actually, it's very interesting because I think he tried to use non-standard analysis even to clean up the proof, but you need to sort of iterate into non-standard universes so much that he claimed the gain in clarity where you conceal all of the epsilons is negligible. So he tried many different non-standard directions. Okay, so here my claim, and using the Zemaretti example, is that impurity can make the reason why particularly explicit. So in this case, so here we have Zemaretti's theorem. It's proved to be equivalent to some ergodic theorem, right? So this is the theorem that models the presence of the arithmetic progressions. The key element in the proof it's called the structure theorem. It's called the Furstenberg structure theorem, which essentially tells us that given an arbitrary measure-preserving system, it can be split up into components that are either highly random or highly structured. And we know how to deduce the recurrence pattern in each of these pieces quite easily. And then we can kick that back down to Zemaretti's theorem, which itself has a structure theorem, which is called the Zemaretti regularity lemma, which is a theorem on graphs. But he stated much of his stuff in terms of graph theory. My ultimate claim here is that moving in this direction produces an explanatory proof, whereas moving in this direction does not. And that's what I want. So my claim is that the impurity in this case, which is both topical in the sense that you might think ergodic theory is rather different from combinatorial theory, and infinitary because the resources here are quite strong. It also helps us recognize, so in calling the structure theorems are supposed to be the reason why the theorem is true, because they're telling you how to split up an arbitrary set or measure-preserving system into pieces you know how to handle, from which you can deduce the arithmetic progressions or recurrence patterns. So the role of the Zemmoretti regularity lemma and the proof of Zemmoretti's theorem, I think it's much less obvious that it's doing this kind of stuff. Whereas in the Furstenberg structure theorem, it's very clear that all you have to do is take such a measure preserving system, split it up in this way, and then get your recurrence patterns. And so in particular, the infinitary resources in the ergodic theory help kind of clean up all the epsilon parameters that you have to mess around with in the combinatorial case. And it gives your proof a much more linear but also modular structure. So you're able to chunk up relationships between just like a few lemmas and theorems in an easy way, whereas that's not so easy to do in this case. And yeah, there's a paper, I think it's called Modularity in Mathematics by Jeremy Avigat, in which he discusses this kind of idea. And so I actually take it that this is quite an interesting instance of this modularity. And I think you get the modularity in the linearity of the proof structure by appeal to appropriate resources that are also infinitary. Okay, so there are a few problems that you might see with this. So first, you might be worried that the infinitary resources are clearing away too much to provide an explanatory proof of the original result, right? So you want to guarantee that you're not losing any sort of data essential to the proof. And I think I've tried to articulate a notion of content that protects you from this. And in this case, that's supposed to be what the structure theorems are doing. You have this latent structure in each case because both domains, this combinatorial domain and the ergodic domain, have the structure theory present. This word is not apropos.
What does it mean, clear away? I have a problem with English. What does it mean, clear away?
Oh, you don't have to you don't have to. Sorry.
Eliminate?
Yeah, eliminate.
Eliminate.
Okay. Right, and so this is the claim that this reason why is preserved across these domains. Okay, so the conclusion of this is that, well, this impure and infinitary setting is actually potentially appropriate for proving this result. Okay, but why is it better than the combinatorial setting? Well, because of the infinitary resources. So you get this very clear classification of structure and randomness in a measure preserving system, and you're able to take, in fact, transfinite limits and appeal to compactness, and all of this is sort of going on in this proof, whereas you can't do that in the combinatorial setting. So the global proof structure becomes much more linear by concealing these differences. Okay. Yeah, so now a sort of issue with the notion of purity and impurity arises too. So I want to claim that the ergodic setting is potentially explanatory because there's shared structural results in each domain, and then explanatory because you're able to get a much more linear proof structure using the infinitary techniques. But you might think, okay, if these two domains actually share content, in what sense is this still an impure proof? So this really requires a further articulation of content. But I first wanted to say that, or I think that kind of the main point here is that the notion of impurity that is typically operative in mathematics, or that mathematicians are using, is a very kind of surface level or intuitive one. Right? You just look at a result that's complex analytic or a result that's combinatorial, and you say, oh, okay, these seem to be ostensibly different things. In order to get these sort of structural content off the ground, you have to already understand this intuitive base level content and then extract the structural results from those. So this is dependent in some way on this initial level of intuitive recognition. So you might think that that requires some notion of impurity, right? And so even though there is some shared stuff between these domains, that doesn't render this a pure proof. Okay, so yeah, so to conclude, this example was supposed to be a finitary statement of acknowledged mathematical import with many different proofs. And we have some meta-mathematical data on the ergodic proof. I should mention there are also other proofs. There's a hypergraph proof by Gowers from the late 90s. And then there's a fourth one that's even more recent. I haven't looked at these, but that might be interesting. So I compared the combinatorial and the ergodic proofs. And then I claimed that the ergodic proof was explanatory because this structural feature that allows us to decompose the entities in question and thereby deduce the recurrence patterns we're interested in is particularly clear. And this was made evident by the linear and kind of modularized proof structure, which you get by appealing to the infinitary resources. Yeah, it's worth mentioning that it does seem that both the topical and elemental impurity are playing a role here, because you might try to prove Zambaretti's theorem in a different, using a different intuitive domain of mathematics. Of course, if that doesn't have the requisite sort of structural features that the ergodic setting has, you might not get a proof at all, much less an explanatory proof. So you're using the topical impurity there, and then the elemental impurity, where I'm understanding that by axiomatic strength, that comes in by providing the nicer proof structure. So both of these things are okay, and yeah, it would be nice here to say more about the elemental impurity. And so yeah, this depends on the result that I alluded to that was claimed by Abigab. So it'd be interesting to see. So this is the tau is the Furstenberg structure theorem. And it seems to be so strong because you are transfinitely iterating like a decomposition of a measure preserving system into pieces. And so the question is, how long do you have to do that for? But that's open. That's okay. So to conclude the whole talk, I've tried to demonstrate the development of this study of finitary statements with infinitary proofs from mathematical logic by the independence results to contemporary philosophy of mathematics, and in particular looking at results from mathematical practice. I tried to show ways in which questions from contemporary philosophy of mathematics interact with this finitary infinitary distinction. I focused on impurity, purity, explanatory and non-explanatory proofs. And then I examined my proposal that impurity of both varieties and explanatory power is supposed to be more intimately connected than has been thought. And I did this via Zambaretti's theorem. And then to bring it completely full circle, so we vindicated Gödel's doctrine formally, because we saw that Fermat's last theorem is in fact sufficiently strong to undermine Feferman's arguments. And then in a modified form, where you think about the necessity of infinity in terms of explanatory power or actual conviction, maybe, that's what I've tried to say that the infinitary proof of Zambaretti's theorem is actually providing for us. So that's a vindication of a sort of modified version of Gödel's doctrine, where you claim that the infinite is necessary for explanation of conviction. Okay. Thank you.
There are questions from the web? Yes, but then we come here. There are questions from the
Zoom.
people on
Okay,
Zoom.
I completely forgot.
People on Zoom. Someone has questions on Zoom.
From the Zoom.
Okay, if not,
Not at the moment.
Christopher Pink.
Yeah.
Yes, so Chris, you can go.
Yes, thank you so much. I really appreciate the opportunity to zoom in, and I enjoyed the talk a lot. Patrick and I have actually had a few conversations about some of these issues, so this may just be a repeated question, but it does seem that the notion of structural content is different from other ways of thinking about content, in the sense that the structural content of a theorem could be initially obscure, and then we figure out what it is, or the proof will illustrate this hidden structural content. And so I just wonder if there's, I wonder if you could say more about why you want to call that feature of the proof, or the connections between these distinct topics, a connection in structural content. Couldn't we just say that Oh yeah, the proof explains because it's talking about these structures, and these structures are related in an appropriate way, and that is the key to how the explanation works, and it helps us to see the sense in which the proof is impure. But the specific choice to think of this as involving structural content is how central is that? That would be what I'd like to hear more. Thank you.
Yeah. So no, thanks for zooming in, Chris. Yeah. So is the question why think of this in terms of content at all? Maybe.
Right. So I mean, we could say that the natural numbers and the rational numbers share a structure, and then of course, they might differ in some other respects structurally, but they have a shared structure, and so some things that we say about the natural numbers carry over to the rational numbers. Now, in your case, the structural the structural features are much more intricate, and so maybe that analogy is not a good one, but I don't feel any inclination to identify the shared structural content in the natural numbers and the rational number case, but I would just talk about, oh yeah, there's structural relations between these domains, and there are these mappings and so on. So that may be more metaphysical, I guess, or maybe more ontic and less cognitive or epistemic. So maybe that would be one way to highlight the significance of the vocabulary, at least as I hear it.
Oh, I think that's
sorry.
Yeah.
I think that it would be very good whether in answering to Chris, you also explain better to us what you mean by structural content.
Yes. Okay. Right. So Chris, I think that is one. I think that's a helpful way of distinguishing what I'm trying to do. I tried to proceed more epistemically rather than ontically, but I also wanted to. Yeah. So the sort of question that I started out with was, okay, so you have some notion of impurity, and you have some notion of explanation, and it's very reasonable that explanation and purity would be connected, right? And my sort of question I posed to myself was, well, sort of how far can you go in terms of impurity and actually retain an explanatory proof or something like that, right? So you might think that, I've seen people claim that, category theory or something can be explanatory. But if you take a sort of thicker notion of explanatory proof as being like, okay, you need to indicate like the reason why something is true, that might abstract from too much of the initial content of the theorem, right? And so I tried to find this kind of like intermediate point where you have shared content, right, that allows an explanation of a mathematical fact to get off the ground, right? But in such a way that you initially have to acknowledge that there's a difference, an intuitive difference between two domains of mathematics. And only after you acknowledge that difference can you see that there is, related content, right? So you can say, here I have a theorem about a sufficiently dense subset of natural numbers. Here I have a theorem about a measure preserving system. I would want to say, okay, whatever, what is the content of this statement? Well, maybe whatever features are true of that set and whatever things are true of that measure preserving system. And then once you actually extract all the things that are true of these entities, you can see that there's some sort of shared structural content. But I guess I wanted to say, like, these, if you have such a set and such a system, in some sense, the theorem is about those sets and systems, and so it's about, in some sense, the structure that each of those things possesses. But the reason to go via content was in order to make sense of impurity and explanation together. But I think you're correct that maybe that's not necessarily the case. Is that a helpful? Does that help?
Yeah, no, thank you. Yeah, I look forward to hearing other questions as well. Thank you.
Other questions?
Yeah, so my question, one question I have is so explanation, right? So it seems to me that explanation often has to do with translation between two languages. And so at least I can think of many examples in mathematics where a proof is considered explanatory because it links to different areas of mathematics, right? And then the explanation comes from the fact that these two sub-areas of mathematics have two completely different languages. Each language is kind of very restrictive, right? So, but they study the same object, they prove the same theorem, right? But every language is very restrictive. So kind of that you can say something in one language that's relevant to the other language, that's a surprise.
Right.
And this surprise then may have something. So my general question is, are there accounts of explainability which kind of center explanations around this idea of explanation as translation between two different languages?
Not that I know of, actually. Actually, Chris would probably be the person to answer that. But yeah, I've not seen it thought about in that way. I think what you're saying, Alex, maybe is so I made this distinction between like a local conception of explanation and a global one. I take it that you're pushing more in a global direction. So I was construing explanatory power as a property of proofs, but you're thinking about, okay, here's a theory in a language, here's a theory in another language, right? We're thinking about how you can sort of translate one into the other, right?
Like probabilistic methods in graph theory, right?
Yeah, okay.
So what's going on here, right? So this is really interesting.
Right.
And
but all I'm saying is that might very well be a different conception of explanation that you have to analyze in different terms because you're dealing with very different entities.
I think it could be interesting to try to say something about that.
Yeah. Well, I think you're saying, okay, you have connection between two different languages, two different theories. It seems like that's an instance of impurity in some sense, right? And then because they can actually intelligibly say things about each other, that's the explanatory power.
Yeah. So
right?
infinitariness and impurity as correlate with explainability, at least in many cases.
This is the claim.
So, what an example of, Alex, this is maybe a really easy example, is to say that Boolean algebras, that coproducts of Boolean algebras exist. If you try to describe the coproduct of two Boolean algebras, it's not easy. If you know Stone's theorem, it's completely trivial.
Mm-hmm.
Yeah.
I mean, completely true, and that's a better explanation for how the coproduct comes about, from my point of view.
Yeah.
Because if I try to do it combinatorially and describe the thing, it's pretty messy.
Yeah, this is actually very nice because you're explicitly saying stone duality is a bridge.
It's an explanatory
between two different languages
of
mathematics.
Theorem.
Like
I mean, not every theorem
topology.
is, right? But some theorems are these bridging theorems that really they explain something in one field.
Well, right.
And I think that's what you were getting at.
Yeah,
right,
absolutely.
yeah.
These are absolutely, yeah.
Well, no, and that is kind of precisely the role that these structural results are supposed to be playing. Yeah, and it's also worth mentioning that the same kind of structural results pop up elsewhere too in hypergraph theory. So the like hypergraph proof of San Bernardino's theorem uses its own kind of structure theorem, and so you do have these higher order things. That are connecting initially disparate looking pieces of mathematics.
So a proof of Ramsey's theorem goes by first proving the infinitary version.
Right.
And that proof uses Tikhonov's theorem from topology.
Mm-hmm.
Yeah.
Now, that should be an example of a pretty impure proof, right? But
action of choice.
But quite explanatory.
Yes, right. Yeah. I think that's good.
It's actually really. I mean, the proof is really beautiful when you put it in those terms. Right. I mean, you prove that you make this gigantic product of, but they're all discrete. They're all finite discrete spaces, but you take an infinite product of those. But because they're finite and discrete, each one is compact. So you have this compact subset, this big compact set, and you prove that the relevant part of that is a closed subset of this gigantic compact space, and therefore is also compact, and then you smack it with something else, and then you're done.
Yeah.
It's pretty, it's pretty slick.
Well, I think that's actually what pushes the Harris Harrington over the top, because you need to use infinitary Ramsey's theorem. That implies Paris Harrington, and you know that infinitary Ramsey is not provable in Piano arithmetic.
Right.
Because of this.
Yeah, because it's very strong.
Yeah.
Right.
Now that's
Although it does occur to me that maybe there's something else to say, because locale theory has a Tikhonov's theorem that doesn't require
yes,
choice.
I need to learn about this. Yeah.
And these are very simple spaces. They're finite
Right,
discrete spaces.
exactly.
If you take the products.
Yeah. Just the products different.
So that product should still be spatial, right? So
Well, as soon as you jump to the spatial, that's when you can use choice, right?
So do you not need
these
choice?
are really combinatorial things. These are finite these are power sets. They're all finite power sets. They're all the frames that you're concerned with. Because they're just power sets of discretes. They're just the topologies on discrete spaces.
Yeah, but then the product, what's the
No,
product?
I know.
To make the product, to think of the product spatially, that's where you're going to jump and use choice. But maybe you can still argue just in locales and get somewhere.
I think you could at least control how much choice you use.
Well,
That way, maybe. Anyway,
So
sorry, that was off kind of.
Well, so if you use locales, you're saying you can control.
I don't know, but
well, you can control choice for that, but whether you can then transfer it and use what you need for Ramsey.
Ah,
Going to the space, and as soon as you go to the space, you use choice.
yeah. So prove that
you'd have
certain
to try and
to prove that a certain
locale
locale
Ramsey.
is spatial typically requires choice.
You don't need full choice.
That's what I mean. I think some control over choice.
Mhm.
It's this, what do they, Boolean
Boolean.
probability.
Yeah.
That's what-
Yeah.
I'm still trying to understand what it means for a proof to be explanatory.
Well, yeah. Okay,
So
yes. That's fair.
I am okay. So maybe I'm going to give you an example, and you can tell me if this is or not.
Well,
And it's going to be more mundane than the.
That's fine.
And the bridge is going to be even shorter because it is between real analysis and classical and complex analysis.
okay. Yeah.
Okay, so sometimes you see a function in a real analysis, a real function, and then you calculate that is expressed by a series, and then you calculate the convergence radius of the series, and then you have a number. But there is nothing apparent that why you should obtain that number as the convergence radius for that function. But when you see this function as a complex variable function, then you see that there's a pole that was an imaginary number, a complex number that was not real, and this is what is limiting the radius. Is that an explanatory?
Yeah, according to so let me say the question about what constitutes an explanatory proof is massive. So I was just going with this very bare bones, like, okay, there seems to be, you try to identify some reason why the thing is true, right?
Mm-hmm.
I think the example you give is precisely that. So just according to this very minimal conception of explanatory proof I'm using, I would say yes. Okay. But there are tons of questions here, right? So I didn't really articulate how you might argue for what constitutes an explanatory proof. Usually you might try to do it via other epistemic virtues, maybe like simplicity of some sort or unification of some sort, right? I didn't undertake that here, but that is in fact part of the project. That's actually a really nice example. That's not so hard. Yeah, I like that. Yeah.
I have a reaction about it and then a critical question. So the reaction about what you say, oh my God. No problem. There is a problem about the explanatory nature of a proof that use tools outside the domain in which the theorem hold. Because it depends on what you call explanatory. If explanatory means that explain what makes the theorem true, the theorem is provable within a domain that is restricted, of course what makes it true is inside this domain. And so if you take something outside the domain, cannot explain what makes it true, because what makes it true is in the domain. I make a much simpler example.
Right, but
you can prove the Pythagorean theorem using proportionality. And it seems that is a very explanatory proof. But of course, proportionality is not what makes the theorem true, because the theorem can be proved without proportionality. So it cannot be proportionality that makes the theorem true. The theorem is true because of question of incidence, of course. But then it depends what does it mean to be explanatory. If explanatory means to explain what makes it true, so I think that your example is not explanatory, it cannot be explanatory. If explanatory means that justify from a higher point of view a certain thing that you see there, that is another story. So your example can be explanatory. But this is a little bit the point that I want to make with
Semerity, I think.
Semerity.
It's Hungarian.
Semerity. I'm dyslexic also this phonetic. So Semerity theorem. I'm wondering whether such a theorem is a good case for your program, general program. Why? Because it seems to me that this a theorem very similar in some sense to Fermat theorem. The sense that the strict content of the theorem in such is very, very, very elementary.
Yes. Right.
So that understanding the theorem is required practically nothing more than to know what is a natural number.
Right.
Even a finite natural number. And what is addition. So it's a very, very, very basic concept.
Well, that's good, no?
Sorry, that's good, but the problem of this sort of theorem is that how can you imagine that a theorem like that has a pure proof? If proof means topically that the proof use only
because it's so restricted.
Because it's so restricted, the content of the theorem, and of course the theorem depends from some combinatorial facts that concern the structure of natural number. So it seems to me that there is a opposition between what the theorem says and what can make the theorem true. In this sense, what makes the theorem true is something that is very mysterious even to us. It is the structure, a combinatorial structure of natural number. That is, we don't know what it is till now. This is what makes the theorem true. But what the theorem says is something very elementary. Is a sort of elementary manifestation of its hidden structure. So a proof, natural, of course, has to go further. And when you say that an infinitary proof is explanatory, it seems to me that the point is here. If you do not want an explanatory proof, necessarily, you need to work in terms of very elementary combinatorial fact. Okay, so when you work with elementary combinatorial fact with few resources, you have to go through all the combinations. And so make a combinatorial complexity that is not eliminable. It's not eliminable because you have to work at this level. You have not a macro level in which you can see the combinatorial fact as a particular manifestation of a general fact. When you go infinitary, now you have not to go through all these combinatorial facts because you look at them at once from another point of view and see this explained. But now my question is, can we take this as an effect of going to infinity with respect to the finite, or simply as a fact
because it's so
to go here with respect to here?
I see.
And the finite and infinite is not really the point. So to find a way to go to see the combinatorial fact from an ideal perspective, from you work on fact that live in the plane, and you go on the mountain to look at them. And so from the mountain you see the plane much better. And the problem is not whether this mountain is finite or not infinite. The problem with the mountain is simply a little bit higher. I don't know.
No, it's a good question. I'm not entirely sure what to say to it. Do you not find it moving at all, Marco, that like there is a combinatorial structural result. Like we have it. It's the context is not so restricted that we can't actually see.
No, the content of the theorem is restricted. The content of the proof is restricted. So I don't know.
But this, yeah, the nothing really is not a ton of content is added when you appeal to.
So I find another way.
No, I see.
I see perfectly what you do. It seems to me that's very nice. But I think that it was also also nice to find another case or other cases
that's not so.
In which you have an elementary, a poor proof. Yeah. You have a clear proof.
Yeah.
And still, you find a non-pure proof, infinitary, that is explanatory.
Yeah.
Because in this case, it's simply not imaginable to have a pure proof, in a certain sense of pure, unless if the notion of pure is a question of domain. So it's impure because infinitary, this is finitary, it is infinitary, so the opposition finitary, infinitary, the proof, the fact that this that is impure depend also simply on the fact that it is infinitary, and this other is finitary. But it does not depend on the particular condition of the theorem.
Yeah.
And one of the discussions that I have a lot of time with Andy is exactly this one. The distinction pure and impure concern the domains and concern the particular content of the particular theorem. And if you concern the domain, it seems to me that is a little bit problematic, because then any transcendental proof is impure. But then you have the distinction is not enough fine-grained.
Yeah.
It seems to me the distinction pure and impure require to be a little bit more fine-grained than simply depend of the domain. It's a proof in ZF in Z2 of a theorem that is statable in Peano, of course it's impure. But it's interesting to say this distinction in terms of pure and impure simply is a proof. So it would be interesting also to have a case where you have a pure proof.
Yeah.
And then by staying within the same domain, you find something explanatory from an impure proof.
Okay, yeah. So you think so move to a somewhat less restricted context?
I have the impression that this distinction of finite and infinite is too macroscopic.
Yeah.
To really deal with the question of purity, impurity.
Right. Yeah. I mean, and as I had to use topical purity in order to make distinctions too. I was using both. Yeah. And it might be the case that you need to make both distinctions in order to argue in this way, because in order to make sense of the impurity, initially the ostensible impurity, you have to use a notion of topical impurity. And then you examine this other elemental impurity where the infinitary, finitary stuff comes in.
And the case of Peano of Fermat is a little bit different, because even if Peter is right that we cannot tell it definitely because we don't know, but we can imagine that is a finitary theorem that are not finitary proof. Okay? And so this is another story. So, for example, Paolo worked very on the desired theorem.
Yeah, sure.
Desired theorem is a nice case of a two-dimensional theorem that are not non-metrical proof that are pure.
Right.
So there you can prove that there is no proof that are pure of this theorem. So in order to have a proof that is not projective, you need to go in another domain.
Yeah.
So possibly also would be interesting, a case where we know that there is no pure proof. So you need to go in pure and to see how far you have to go in order to find the proof.
And yet something
and
that
the case of
right. And yet something that is not an independence result.
It is not an independent result.
Yeah, exactly. Okay, I see. Yeah. No, that's
Other questions
on
from
the
the
point of purity and infinity, and one has to make assumptions. So if pushing on this point is not welcome, I'll be happy not to. But
pushing on any of my points is not welcome.
Then I'll just dive in. So I wonder if it seems to me one of those beginning assumptions is that there's some impurity between the finite and the infinite. So
I think that's plausible.
yeah, it's totally plausible, but I wonder, one can ask, there are different conceptions of the infinite. So the potential infinite might not be impure with respect to the finite, whereas the actual infinite Might be.
Yes.
Also, I wonder.
Yeah, that's part of why I made that initial distinction. Where like I'm calling
This is
finitary
it,
mathematics
right here, yeah.
and infinitary mathematics.
Yeah, yeah, and no, it's as long as it's clear.
But no, yeah, I agree. You could ask these further questions. What you mean by finitary, infinitary?
Well, and also, I much less clear to me what is the finite foreign with respect to the does it go the other way?
Does it go the other way? Yeah.
Is it symmetrical between the two? You could say the finite is included in the infinite, but if there's a difference in kind, shouldn't that be symmetrical? Shouldn't they be mutually impure?
Yeah, I mean that is interesting. I guess again here you'd have to say something like, well, the ascription of purity or impurity, you do this for like propositions, right? So you need like some further like syntactic structure to be saying something isn't pure. Whereas yeah, like the thinking about I take the point that thinking about the relationship between finite and infinite seems to be impure in one direction but not the other. But that's maybe too broad a way of thinking about what counts as pure or impure. I don't know if that's a very good answer to your question, but that's kind of what I would want to say. Yeah.
Sure.
But no, it's. I mean, also, this is kind of related to something Marco said yesterday, right? Like, okay, you have a theorem of piano arithmetic. Certainly, you could prove it in second-order piano arithmetic, right? But that's not the kind of thing we're interested in. We're interested in kind of these more naturally occurring proofs that use stronger stuff, rather than just thinking about it formally in terms of strength right away.
And I have another question. So your distinction, finite and infinitary, piano first order, piano second order, make me think about it. So your proofs that you make in piano second order, that you cannot make in piano first order because they use an instance of comprehension. Like they are an instance of comprehension, necessarily you cannot do that. But this instance of comprehension can be a very simple one, even predicative, and they use only that. So you are still legitimate to call it infinitary, just because it uses a very simple particular tool of second order piano arithmetic. In other terms, any proof in second order piano arithmetic is infinitary, just because it is in piano second order arithmetic. Because it uses.
Well, if it essentially uses the comprehension, right? I mean, this is. This is why
essentially use the comprehension.
Right, but this is why you can actually look at the different subsystems. I mean, this is where the reverse mathematical stuff becomes useful, right?
Yeah, exactly.
You can actually calibrate strength a little more finely. Yeah.
Exactly.
So you don't have to just make this very broad appeal to second order piano and first order piano. Right? Yeah.
For example, in the talk that I gave at the beginning of the seminar about the Frege definition of real number, in the definition you use a comprehension, but you can eliminate a lot of comprehension and do it the same simply by abbreviation. You don't need predicate. You simply do. That is a technical that is very, very often used in reverse mathematics.
Sure.
Is what they do in time, because otherwise they could not go. Okay, so this means that when you use comprehension instead of a formula, but in fact it's real infinitary.
Yeah.
It's infinitary, yes, because it's quicker.
But in some sense,
it's quicker. But in some sense,
uninterestingly infinitary.
It's not interestingly infinitary.
Yeah. Well, I mean that's exactly that's. So like the Feferman paper is like, is infinity necessary? Well, we have these results that are independent of piano arithmetic, and then he acknowledges, you do require in some sense, infinitary power to prove them, but the systems are predicative, or you can use, intuitionistic logic, and so they're still epistemically safe.
Exactly.
Yeah.
Exactly. So my wonder is whether the decision of finite infinity is not also more fine-grained.
Yeah. Well, I think you would want to layer these further distinct. I mean, right. So you would say, okay, finitary infinite. Then you could layer on top, look at predicative versus impredicative, which is precisely what I wanted to do here, right? So if we have the structural theorem and it's equivalent to Pavlov comprehension, okay, great. That's in predicative mathematics. That seems much more serious, right?
Yeah.
So this is where the reverse mathematics would be very useful to have. Yeah.
Yes, more than reverse mathematics, the reverse attitude. because the reverse mathematics, reverse mathematics is a very particular problem.
Yeah, sure.
A program where you go on the other direction in order to find the existential assumption,
Yeah.
let's say theoretical
Yes.
existential assumption. But we can also be interested in going on the other side to find the less explanatory, less pure, less economic.
Right.
So the attitude is not necessarily concerned with the existential import of your action. You can have the same attitude, the reverse attitude, that focus on other sort of assumptions
Yeah.
that you make and that you could eliminate.
Right. Right. Yeah.
Other questions from the web?
Oh,
No.
let me check the Zoom. No.
No.
What is on slides 34 to 38?
References if you want them. Yeah.
Hey.
Yeah. Anyway, yeah, there you are. Of course.
Okay. Thank you, Patrick. Thank you very much.
Thank you all.
And
Thank you for